So for everybody watching this live, I do have the chat function in Zoom open. So you can feel free to ask me questions there. But today we're going to be discussing postulates and diagrams, the next lesson. Euclid in Elements discussed a number of postulates. He started with some definitions, and then he also created postulates in a way that he was deductively reasoning to build the universe of geometry. From postulates, he was able to expand a little bit further to theorems. All right, so first of all, we haven't really defined together what a postulate is. So let's talk about that. I have discussed postulates in class, and what I've said about it is that it's effectively something that is a self-evident truth. Your textbook defines a postulate. Let's go ahead and get that spelled properly. Your textbook just defines a postulate as a rule accepted without proof. Or I like to think of it as a self-evident truth that we don't need to prove what the rule actually says. There's a handful of these that we are going to work with, but to identify a postulate is a pretty difficult endeavor. The reason why is because if you can look at something and it may not have a self-evident truth about it, and it might not just be true for, from the onset. Think about what a difficult thing that is. Just even thinking about the notion, because we have inductive reasoning, right? Where all we need is a single counterexample. Like, for example, the sun will come up tomorrow, right? That we accept to be true. The sun will come up tomorrow. However, it's not necessarily true, right? We only need the counterexample, how rare it might be that the sun may not come up tomorrow. The issue, there might be something in the universe we're not accounting for that could terminate this, the truth of that notion. For a number of reasons. Supernova could randomly happen, asteroid could hit the Earth, or, whatever. But as infinitesimally small as that is, it takes away from the truth of that statement, right? So that is not necessarily a true statement. That's the difficult thing about that. From what we know scientifically, that is incredibly unlikely to happen. But again, that's where we're getting to with some of these things that have potentially not truth about them. So the textbook goes about actually numbering these postulates. The first one we're going to discuss today is what they call is 2.1. By the way, I'm going to tell you guys to not necessarily cite these things via number. And the reason why is because if you cite the wrong number, that's problematic. Okay, so our first postulate is the two-point postulate. And I'd rather that you name these than number them. If you cite the incorrect number, you will be incorrect. Okay? The two-point postulate says that through any 2 points, there is exactly one line. Versus the line-point postulate, which says something similar. It says a line contains at least 2 points. So those are our postulates with regard to lines. Next, we have the line intersection postulate. The line intersection postulate says if 2 lines intersect, then their intersection is at exactly 1 point. So things that we can look at and understand to be self-evidently true. The 2-point and the line-point postulate are very similar. I'm actually pretty forgiving when you guys mix those two things up when citing them in a proof. Okay. The next is the 3-point postulate, which also we're going to group with another postulate, the plain point postulate. What this one says is that through any 3 non-collinear points, there exists exactly one plane. It's so important that we identify this word here, non-collinear, right? Because think about this. All we're trying to figure out is one counterexample. I have one for you. Ready? Here's a line. 1, 2, right? Right now, that's our 2-point postulate, right? Or the line point postulate, right? So this shows that we have a line with exactly at least 2 points, right? Or with the 2 points, we can just take only one line through it. Now, that line, of course, is different than this line. Here's 2 other separate points. Or even this, if I were to put a point out here, this line is a separate line, correct? But here, if I put a 3rd point on that line, that is a collinear point. So we have 3 collinear points. Now think about when it says there's exactly one plane. Well, how many planes could you put through that point? Or excuse me, how many planes could you put through that line? The answer is it's infinite, right? You could put an infinite number of planes through that. Just think about a piece of string, right? Like a piece of string or a piece of yarn. How many ways could you slice a paper through that, right? And it's in an infinite number of ways. It's just one of those things that would be rotating, right? So we can only have, or these 3 points have to be non-collinear. It works like this. 1, 2, boom. I can make up a line through there, right? There's exactly one line. And then if I have another point that's non-collinear, well, I'm not going to have a line that is simultaneous, right? Because, for example, think about this. If I put another point here, well, that's the same point. That's the same location, because think about what a point is, right? Additionally, those would be collinear, right? Because I have through one point, or through one, I'd have one line that can go through there. But the second I move to a 3rd point, right, that makes it where I can't only put one line through it. And if I can only put one line through it, then I can put a multitude, an infinite number of planes. Moreover, we can have the plain point postulate, which is effectively saying the same thing. It's going to be phrased differently, and as we've seen, the converse to a statement, right, which a lot of these are seemingly like converses, the converse to a statement isn't necessarily true, but here we have to clarify anytime that it does. So here, a plane contains at least 3 non-collinear points, right? So any plane that I have, you just take a piece of paper out, right? I can't just say, oh, the minimum number of points is 2, because that would just be a line. And if there's a line, it means I can put an infinite number of planes through it, right? I hope you're now able to see, as we spent so much time in the last week considering logical statements and how we were forming these things, right? Converse, inverse, contrapositive, conditional statements, truth tables, and so forth. How that way of thinking, that deductive reasoning is so critical as we're jumping into how we utilize that with discussing geometry. The next one is the plane line postulate. Don't worry, we only have, I think it's 7 of these today, so we're almost to the end, okay? So these are kind of like our basic building blocks that we're going to work with in this course. And we have two points lie in a plane. Then the line containing them lies in the plane. Okay? So it doesn't mean that we have to define the third point, right? If I have a plane and then I identify 2 locations within it, right? 2 points, that's what points are, they're locations. Then they have to be in that plane. I know that sounds kind of redundant, but you know, it's again, that's what makes it a postulate. It's self-evident. Of course it's true, right? And then of course we have now the plane intersection postulate. I was just looking at a newspaper this morning. Newspapers, when you fold them, right? When you fold them, they're like you like have a gigantic plane, right? Or even if a book, you should have a notebook in front of you. Well, think about the spine of that notebook. If you were to unfold the notebook, even when you open up, right? Open it up a portion of the way, you have a plane, right? It looks like a plane. It has thickness, but you can imagine one of the pages is a plane. And then on the other side there, you have another plane, right? You have 2 planes. Just think about 2 pieces of paper cutting at each other, and where they do so, then their intersection is at exactly 1 line. So where lines intersect at a point, planes intersect at a line. The exercises that you're going to go through for this lesson are a little bit different, okay? I'm going to be available as you guys complete this assignment. If you have any questions, of course, you can email them to me. But this is the beginning of us discussing postulates. There's actually a bunch of postulates that you already know, and you just don't really know it yet. They're already actually stowed away. We're going to talk about those soon with the algebraic rules that you already know that we can apply here as we start to do some proofs. It's a difficult notion. Euclid gets into trouble very quickly. There's a notorious postulate, Euclid's 5th postulate, postulate 5th, right? He doesn't get very far, and he already starts to stumble a little bit when he writes elements because it has some problems. It might not be so self-evident. So go ahead and complete this assignment. Good luck.